So let's get started now. In lecture 3, I was asked, question came up, if you change the quadratic non-residue B that led to the C, that was the number you used to carry out the Tinelli-Shanks algorithm, how does do the different B's, how do they relate to the possible solutions of x squared equal A? And off the top of my head, I said, well, I think if you change B to minus B, and then C turns into minus C from the method of generating C from B, then you're going to get the other solution. So I talked to some people after the lecture over the course of yesterday, and I had made a mistake. The example I used to illustrate the Tinelli-Shanks algorithm had a feature that general examples don't. And so basically the bottom line, without getting too much into the details, is it is possible for some instances with the Tinelli-Shanks algorithm that you're always going to get only one solution no matter what B you pick. And basically, it's kind of like this example at the bottom. Suppose you wanted to solve x squared equals 3 mod 13 by the Tinelli-Shanks algorithm. Notice 13 is a prime that's 1 mod 4. So this is a meaningful thing to do. So if A is 13, A is 3 and B is A is 3, P is 13, that you always start by generating an x1 and a y1 that have nothing to do with the choice of B. But in this case, what happens is y1 is 1, and so the algorithm actually terminates right at the start. 9 is a solution, right? 9 squared, 9 is minus 4 mod 13. So 9 squared and 4 squared are the same. They're both equal to 3. So the Tinelli-Shanks algorithm terminates, and you're not even going to use the B. So any B you pick, you're going to get the same answer because it in fact plays no role. So what I said yesterday was not correct. All right. Moving on. New topic. So what can be said about the values of the Legendre symbol as P varies and A is fixed, not the number 0. So, of course, one option is maybe A is a perfect square in the integers. So what does that imply about the Legendre symbol, A on P? What? It's always 1.
Unless it's P squared.
Unless, equals 1 if P does not divide. I'll be pedantic, 2A. I mean, I wouldn't be talking about the Legendre symbol when P is 2. Well, okay. There's an extension called the Kronecker symbol that allows P to be 2. I do not want to get into that. But in any case, yeah, please remember, if you have a perfect square in the numerator of a Legendre symbol, don't instinctively say, oh, it's 1. Watch out. Make sure that thing is non-zero mod the denominator. Then, of course, it's 1. So the Legendre symbol is essentially always 1. Finitely many exceptions, it's 0. So essentially always 1 if A is a square. Now, if A is not a square, it will be a square mod P infinitely often. A and P will be 1 for infinitely many P, and one way to think about that, in fact, is that there's a quite general theorem about how often polynomials vanish mod primes. If you have a polynomial in z bracket x, it's non-constant, then the congruence f of x congruent to 0 mod p has a root. I mean, of course, a root in the integers mod p for infinitely many p. And you can apply this. So as a reference, of course, since everything's been asked on the internet already, you can just go to Math Stack Exchange question 1019538. You have to be careful when you make a record of these question numbers, because I also had a Math Overflow page on this topic, but of course I checked that the pages are correct, and my Math Overflow question number was wrong, and now I can't find it. So if you find a Math Overflow question on this topic, please let me know. In any case, there's a reference if you've never seen this argument. It's a very elementary argument on the level of Euclid's proof of the infinitude of primes. If you have a finite number of primes at which your polynomial has a root mod p, there's a way to systematically show that there must be an additional such prime. And so what you're going to do is you just apply this result to the polynomial x squared minus a. Because if x squared minus a has a root mod p, a is a square mod p. The Legendre symbol is 1 if p doesn't divide a. So the fact that the Legendre symbol of a non-square, like 3 on p, is 1 infinitely often. So this is really just an instance of any non-constant polynomial over the integers has a root mod p for infinitely many p. The fact that the Legendre symbol is infinitely often minus 1 is a different story. If a is not a square, then the Legendre symbol is minus 1 for infinitely many p. I'll just give you a reference for proof of this. You can see the nice book by Ireland and Rosen. I think it has page 57. Page 57, the second edition. I don't think anybody has the first edition anymore. So it's an inductive argument. I mean, if you have a finite list of primes, in any case, it gives a method then of finding an additional prime, so you can show that this happens infinitely often. I will make a comment. So they prove this by using property of the Legendre symbol, quadratic reciprocity. I will just say the proof can be made simpler using the extension of the Legendre symbol called the Jacobi symbol, which I don't think I've ever talked about. I had grand plans to have a whole lecture on using the Jacobi symbol, but that didn't happen. So in any case, there's a reference for you, and as an exercise, whatever. So there is a proof out there you can find, and there are other ways of approaching it if you have other techniques available. And in fact, it's worth noting that if you use Dirichlet's theorem, if you use quadratic reciprocity plus Dirichlet's theorem, by Dirichlet's theorem I mean the theorem about the infinitude of primes in arithmetic progressions when the first term and the common difference are relatively prime, using these two results, you can show that in various senses, the density, I'll write delta for density, the density of primes for which the Legendre symbol is 1, and the density of primes for which the Legendre symbol is minus 1 are both 1/2. Okay, you can see this numerically. If you were to say to count, like a is minus 1, you're comparing primes that are 1 mod 4 versus 3 mod 4. If you count up to a large number, the primes that are 1 mod 4 up to that amount, or 3 mod 4, you'll find it's 50-50, to a pretty good approximation. So in the limit, both symbols take on the two values as p varies. The point here is we're letting the denominator vary, not the numerator. The denominator varying is a more subtle thing. And they basically both occur not just infinitely often, but in some sense an equal amount of the time. All right. So I would like to show you an application of this third aspect, Legendre symbol for a non-square in the numerator and varying prime in the denominator is minus 1 infinitely often. I want to use this to do something in non-commutative algebra. All right. So we're going to do an application to division rings. Everybody heard of a division ring? What's a division ring? It's a ring. Very good. Yeah, it's like a field that may not be commutative, right? So a division ring, we can convey the idea by saying it's a possibly non-commutative field. So we just take all the conditions for a field, and we remove the condition that multiplication is commutative, but we do retain the existence of multiplicative inverses, the same multiplicative inverse on both sides. Like in group theory, the same inverse works on both sides. So possibly non-commutative field. So what is example of a division ring that you know besides fields? Right, so the example historically first, and I think for many mathematicians who don't explore certain areas in algebra, the only example that they ever heard of is Hamilton's quaternions. So what does that look like? It's written as H in honor of Hamilton. It's four-dimensional over the reals, R plus Ri plus Rj plus Rk. And the rules are going to be that I squared is minus 1, j squared is minus 1. K is equal to ij is equal to minus ji. I and j anti-commute. And from that, you can derive that k squared is minus 1. And then it's hard to remember the rules. So ij and minus ji are both k. And then what you can do is you can draw a little circle, I, j, k, little arrows in alphabetical order. And so the rule here, so I times j, if you take a product of two of these terms in the direction of the arrows, it's the third term, and if you go against the arrows, it's the other number negated. So for instance, I times k goes against the arrow, so it's minus j. K times I goes with the arrow, it's j. We have ij, ji, ik, ki, and then we just need jk. J goes with the arrow, so that's I, and kj goes against the arrow, so that's minus I. All right, so this little diagram helps you to remember. You might be on the proverbial desert island and you need to multiply quaternion. Yeah. All right, so the important point here is that if we take, so it's a ring, it's associated for multiplication, and so for any quaternion Q, A plus BI plus CJ plus DK, A, B, C, and D are real numbers, we set the conjugate of Q, A minus BI minus CJ minus DK, and then we might even set the norm to be the product, which in fact, although the ring is generally non-commutative, I and J don't commute, Q and its conjugate do commute, the product is the real number, A squared plus B squared plus C squared plus D squared, which of course is positive if Q is not 0. So Q has inverse the scalar 1 over norm Q times Q bar. All right, so this is a division ring. Other thing to comment on, the only elements that commute with everything are the real numbers. So as in group theory, the stuff that commutes with everything is called the center. So the center of H is the real numbers. We call it an R-central division ring, or a finite dimensional R-central division ring, dimension 4. And you can also, if you can write it in this clever way, R plus Ri plus Rj plus Rk. If I make it R plus Ri, and I can factor a j on the right. So you put the j back in, you get your Rj, and your I times j is k. And then, you see, this becomes C plus Cj. So you could think of H as a left complex vector space with the rule that if you find a complex number on the other side of J, you can put it on the left side by conjugating. So you can check that. You just write Z as A plus BI, and you just verify this is true. So you can kind of simplify the appearance of H and collapse it down to make it look two-dimensional over C. All right. And although the quaternions were discovered kind of almost by accident by Hamilton, I mean, he was trying to do certain things, but it was not discovered for conceptual reasons. But let's see, that was 1848. So 20, 30. Anyway, 25 years later, Frobenius proved that there is a role, a kind of a singular role for the quaternions in mathematics. Oh, dear. This is the most annoying thing. Theorem, not the theorem. This theorem is great. So Frobenius proved that the only, can I write the word only? The only finite dimensional R central non-commutative division ring is H. So even if Hamilton had not accidentally discovered the quaternions, they would have eventually been found by the people who were tried to make a study of division rings. Of course, the whole motivation for studying division rings was the discovery of the quaternions earlier, so kind of circular argument there. Anyway, it turns out if you replace the real numbers by, since we've had another course on involving p-adics, if you replace R by QP, for QP in place of R, we have finitely many QP central division rings of each dimension. In some dimensions there are none, but in any particular dimension there are only finitely many, and one non-commutative four-dimensional QP central division ring, just like the real numbers. So I'll tell you for p equals 2 over Q2, the only four-dimensional division ring whose center is the two-adic numbers. It's the quaternions with Q2 coefficients. But if p is an odd prime, the quaternions with QP coefficients are not a division ring. In fact, they're the 2x2 matrices over QP, that other four-dimensional non-commutative ring, which is definitely not a division ring. So in any case, so if you just stick to dimension 4, the story actually for R and QP looks the same. But unlike R, you can have QP central finite dimensional division rings of a very high dimension, 4, 9, 16, any perfect square. There are lots of them. I think there are phi of n of them of, there are phi of n minus 1 non-commutative. In any case, yeah, so you have the, but still finitely many of each dimension. So what I want to look at now is division rings whose center is the rational numbers, okay? And we want to jazz up the construction of the quaternions to a more general thing. So let's do that now. So I'm going to tell you what the notion of a quaternion algebra over a field definition. So I'm going to make this concrete, and so I'm going to have to avoid fields of characteristic 2, which pains me very much, but field f of characteristic not equal to 2. Everything I say can be done in characteristic 2, but you just need better ways of thinking about things. For a field f of characteristic not equal to 2, a quaternion algebra over f it's a ring where it's going to have dimension 4, f plus, I'll use the same notation Hamilton did, although it might look kind of funny when I show you the multiplication rules. F plus fi plus fj plus fk, where I squared, call that a, is a non-zero number in f. J squared, I'll call that b, is another non-zero number in f. They may be the same number. And k equals ij equals minus ji. And so then if you actually multiply k with k, writing it in these two ways, you can work out that k squared is going to be minus ab, another non-zero number in f. And so we denote this thing, this four-dimensional thing. Notice it's non-commutative because I and j and I differ by a minus sign, and minus 1 is not plus 1 when you're not in characteristic 2. So we denote this by ab sub f. It's determined by the numbers a and b. The multiplicative behavior is determined by a and b and the field. So for example, let's take a look at the quaternion algebra over Q built out of the numbers 2 and 5. So it's going to be a four-dimensional ring over QQ plus QI plus QJ plus QK, where I squared is 2. I know you think, oh, I squared should be minus 1. I squared is 2. J squared is 5. And k equals ij equals minus ji, and that k squared is minus ab is minus 10. All right. So just like I showed you, the Hamilton quaternions can be thought of as a two-dimensional vector space over C with a funky rule about how j multiplies with complex numbers. We can do something similar here if I again have q plus qi and then q plus qi factoring out a j, because you can put the j back in and then I times j is k. So this sum of independent terms is the same thing as the previous one. But now if you look at the I squared is 2 and you have q plus qi, what is that thing going to be? This is going to behave just like q root 2. So you can think of this four-dimensional thing over Q as two-dimensional over Q root 2. And just as before, when I said J times Z is Z bar times J, here we have J times alpha is alpha bar times J for all alpha in the field Q root 2. Alpha bar is the conjugate element, x plus y root 2 to x minus y root 2. So you can move elements in Q root 2 to the other side of J by conjugating them. Now, I just presented you a ring. It is not at all obvious that this is going to be a division ring. So let me first just tell you some general properties of this construction, which does not have to be a division ring. It's going to be four-dimensional. Sometimes this thing could turn out to be just the 2x2 matrices over F, that more famous four-dimensional ring construction. So non-commutative ring construction. So let me just mention two properties before we come back to this example. So first of all, because of the symmetry because you can swap the roles of I and j. K is j times I, minus j times I. Anyway, you can easily see if you build the construction with the roles of A and B flipped, you're going to get basically the same ring back up to isomorphism. Another property, if one of the numbers is 1 in the construction, this four-dimensional thing really is the 2x2 matrices. And in fact, if this construction is not the 2x2 matrices, By the way, property 2 is not if and only if. You can have numbers, you can have A, B, this construction lead to the matrix string without A and B being, neither one being 1. I'm just giving an example there. So for 3, if this construction does not lead to the 2 by 2 matrices, then it must be a division ring. All right. So now it's time to give you a condition under which this construction over Q is going to be a division ring. And this is going to involve Legendre symbols. So theorem. If you have an integer, not 0, and an odd prime, P, this construction of the quaternion algebra using the numbers A and P, how about this? I'll say it this way. If the Legendre symbol is -1, if A is not a square mod P, this construction that I've shown you actually is a division ring. The study of quaternion algebras is sort of like studying non-commutative quadratic fields. A lot of properties of quadratic is you have the real case and the imaginary case and the structure of integral elements and the study of units and things. So you can do all these things with quaternion algebras. They have dimension 4 instead of dimension 2. But there's a lot of properties of them kind of resemble behavior of the family of quadratic fields in any case. So there's a criterion. I'm not saying it's if and only if, but it's a criterion for determining that such a construction is a division ring. And so as an example, since we know that 2 on 5 is -1, that shows that this construction with 2 and 5 over Q is a division ring. Okay, so we've just built ourselves, for sure, a division ring besides the Hamilton quaternions, but using rational coefficients. If you try to use real number coefficients in this construction with 2 and 5, you're just going to get the 2 by 2 real matrices. It's not going to be the Hamilton quaternions. Now, what about, as another example, so 3 on 11 is -1. That is false. That's very false. 3 is 25 mod 11. 3 on 11 is 1, but 11 on 3, that's 2 on 3, is -1. So this construction with 3 and 11, the quaternion algebra, I already pointed out, if you switch the roles of A and B, it's an isomorphic ring, and so you're going to get a division ring by taking A to be 11 and B to be 3, not A to be 3 and B to be 11, just to be able to detect, oh yeah, it's a division ring by that theorem. All right. Okay. And it turns out, actually, that if you have odd primes, P not equal to Q, this construction is a division ring if and only if one of these Legendre symbols is -1. Okay, so necessary and sufficient that one of them has to be -1. So it's not an accident in the second example that one of the symbols was 1, but the other is -1. It turned out to be a division ring, and it's always going to be what happens when you have, well, this is for odd primes. Yeah, for 2 odd primes. At least one of those. Maybe both, but in any case, at least one of them. Okay, so now here's the big theorem about what we would really like is to be able to find multiple examples. Like there are infinitely many quadratic fields. Q join root 2, Q join root 3, Q join root 6, Q join root 7, lots of quadratic fields. And so here's a criterion that we're going to see can tell us, in fact, unlike real division rings, unlike p-adic division rings of a fixed dimension like dimension 4, there are infinitely many division rings, there are infinitely many quaternion algebras over Q. And so here's the condition for that. If you have an integer a and distinct primes, maybe I'll make them odd for simplicity, distinct odd primes, p and q, if these two Legendre symbols are -1, then these quaternion algebras built from A and P and A and Q, these are non-isomorphic quaternion algebras. So because we know, yes, right. Of course, if the symbol is ever going to be -1, A is not a perfect square. Yeah, right. So great. So for example, we know that there are infinitely many primes that are infinitely many primes P are 3 mod 4. We saw that in the first lecture. We didn't need quadratic reciprocity for that. For that, we used the 1 mod 4. That was for the 1 mod 4. Infinitely many primes are 3 mod 4. So all the division rings built with -1 and P, as P runs through those primes, are, so all of these for such P are non-isomorphic. So there are infinitely many non-isomorphic division rings, and you can use this with any A. Okay, so for all integers A not equal to a perfect square, looks like a perfect trapezoid. Not, what was that? Not equal to a square. Boom, 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 boom. For all A and Z not equal to a square in Z, I had said earlier that there are infinitely many odd primes such that A on P is -1. So we get infinitely many non-isomorphic division rings using this construction. And just like before, when I had the construction with 2 and 5, it can be thought of as 2-dimensional over Q root 2. So this can be thought of as 2-dimensional over Q root A with J squared equals P, and J alpha is alpha bar J for all alpha in Q root A. So essentially this Q root A could be any integer that's not a perfect square. Q root A could be any quadratic field. So this is showing you not only do you have infinitely many non-isomorphic division rings of dimension 4, quaternion algebras over Q, but every quadratic field is inside of infinitely many different non-isomorphic division rings. So there are tons and tons and tons of examples. You can find any particular quadratic field inside infinitely many of them. So the story is totally different. If all you ever heard about was the Hamilton quaternions, you'd think the theory of division rings is some silly little thing. But no, 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 no. If you allow yourself to have coefficients only from a number field, Q, or a finite extension of Q, you get tons and tons and tons of examples. So anyway, so thanks to knowing that the Legendre symbol is -1 infinitely often, for any one particular A, we get such results. That's kind of neat. Anyway, are there any questions? Yes?
So, like, I guess this phenomenon with the Legendre symbols being kind of the behavior of the quaternion algebra, is that like come from, or would it tell you about like
Okay, so quaternion algebras and quadratic forms are very tightly related independently of this. They're all mixed together. So if you know some stuff about quadratic forms, maybe you can say some stuff about these. I would just say it all merges together as one big topic. But I don't want to discuss quadratic forms for this. Yeah. Yes?
So with number fields, we think of, or we can think of number fields as sitting inside algebraic closure of Q, and
I'm sorry? We can think of number fields as sitting in the algebraic closure of Q. Yes?
yeah, so we study like the Galois group of that, and number fields as sitting inside of C. Is there a similar story here where we think of these all as sitting inside some algebraic?
You don't really have the problem, algebraic closure of a division ring is kind of isn't really a thing. Meaning you can't, well, let's put it this way. Even inside of this one example, to talk about like what is an integral element going to be, the sum of integral elements doesn't have to be integral if it's just supposed to be the root of a monic polynomial over Z. So you kind of have the whole thing gets much more complicated. There's not really an analog directly of algebraic closure. You don't. You might want to extend the coefficients to a larger field and pick up some phenomena that way. If you have an algebraically closed field in the role of F, this is just the 2x2 matrices over that. So it's not interesting at all. Yeah. So, anything else? Yes.
The fact that there were finite many division rings in each dimension over Q,
Yes.
is that reflecting the fact that the Brauer group has finite n portion?
So the question is about a connection between the division rings and the Brauer group of QP. Yes, these basically, yes, these are very closely related. Yes. Yeah. But I don't want to discuss Brauer groups during the lecture, but we can talk about that later. Yeah. Anything else? All right. So I want to now switch gears completely and talk about quadratic reciprocity over over other fields. So let me remind you of a result that came up last time. So last time we had this result that if the quadratic ring Z root D has unique factorization, if it's a unique factorization domain, and P is a prime number, D here is an integer, not a perfect square, then there's an equivalence between D being a perfect square, mod P, and 1 of plus or minus P being x squared minus dy squared. And the business with the minus sign sometimes is necessary. I gave you an example with 3, with D being 3 and P being 11. 11 is not x squared minus 3y squared. It can't even work mod 3, but minus 11 is. It's 1 minus 12. So you can get rid of the minus sign. Whoops. You can remove the minus sign here if minus 1 is itself of this form. You can then just show that you can massage out the minus sign. If minus P has this form, then P does as well. Of course, if D is a negative number, the right side is positive, and so the left side could only be P, but I'm saying if D is a positive number, there is a sufficient condition to avoid the minus sign if you don't like it. If you can write minus 1 in this form. Yeah. Okay. So this, of course, this statement, the equivalence here has nothing to do with quadratic reciprocity. Quadratic reciprocity lets the left side become a practical condition of determining what P fit that. It's some congruence condition on P, on the left side. P mod, usually 4D, maybe mod some factor of that, but in any case, so that's kind of, quadratic reciprocity is behind the scenes. It makes the left side look practical, right? If the left side were like, 2 has to be a cube mod P, like, what's that? It's some strange set of primes, hard to describe other than it is what it is. But saying something's a square mod p is a nice property of p. It's a congruence condition on p because of quadratic reciprocity. So now let us replace z root d. Let's replace the integers. Right? We had integers here. Quadratic ring over the integers. Let's replace z with z bracket I. Okay, so in the integers, plus or minus 1 are the units. In z bracket I, the units, now we're getting messages on top. This is what I was afraid of. If my mother writes, oh, it's a video. Hi, Mom. All right, units equal. When my phone said your tablet is now linked, like, oh, I'm going to regret this. All right, so replace z with z bracket I. So the units now are plus or minus 1 or plus or minus I. What are the primes? I'm not going to, no. So primes in z bracket I. So you have 1 plus I is the only prime factor of 2, right? 2 is 1 plus I, 1 minus I, which look like there are 2 prime factors of 2, but 1 minus I is a unit minus I times 1 plus I. You can check that. If you multiply them out, you get 1 minus I. So 2 up to a unit is really, it's almost like the square of a prime. So it's really up to units, just 1 prime factor of 2. And then the rest are what I will simply call odd. They simply are not factors of 2, or you could say they have odd norm. Okay, the norm of a plus bi is a squared plus b squared, and so all the other primes. So some examples here, examples of such primes. I don't know, what do you have? 1 plus 2i, 2 minus I. Well, that's actually a unit multiple of, that was ridiculous. 1 plus 2i, 1 minus 2i, 2 plus 3i, 4 minus I. Some integers, 3 and 7, minus 11, or 11, doesn't really matter, plus or minus. Anyway, so the various primes in the Gaussian integers. How you determine that something really is a prime is a story I don't want to get into. And so let's introduce the Legendre symbol. So if I have an alpha, if I have a pi as a odd prime in z bracket I, and alpha is any element in z bracket I, we set the Legendre symbol, alpha on pi, to be 1 if alpha is a square, and we're not, pi is not a factor of it, minus 1 if alpha is not a square, and 0 if alpha is divisible by pi. So just like the ordinary Legendre symbol. And then we have analogs of Euler's congruence. And maybe I should say here, because the size of z bracket I mod pi is the norm of pi, important combinatorial meaning to the norm, it's the size of that ring. We have an analog of Euler's congruence. The Legendre symbol is congruent to alpha to the norm pi minus 1 over 2. Okay, that's like a on p is congruent to a to the p minus 1 over 2. And from that, you get the total multiplicativity of the Legendre symbol. Alpha on pi, alpha beta on pi is alpha on pi beta on pi for all alpha and beta in the Gaussian integers. And because of the multiplicativity of it, to calculating a Legendre symbol in this setting is reduced to you might call kind of the main case, pi prime on pi for, well, odd primes pi and pi prime that are not unit multiples. I don't want to say distinct because if the unit multiples, the main law doesn't use that. In the integers, we just take positive primes. So we don't really think much about it. Distinctness, there wouldn't be unit multiples because they're both positive. But here, for odd primes that are not unit multiples, any formula for that in terms of pi on pi prime. And then we have the supplementary cases. So this is related to the even prime. Well, maybe I'll do first for the units. First for the units. I on pi. And then 1 plus I on pi. So formulas for these, this would be a kind of a quadratic reciprocity law. Okay, so I'm not going to give the details here, but you could say the main law says pi prime on pi, it's some power depending on the exponents, right? T of pi pi prime of pi on pi prime. So you can flip them up to a minus sign where this, I'll just say that these, this exponent here. So how is the sign in the quadratic reciprocity law, how does that depend on P and Q? Meaning, what does it really depend on about P and Q? In the main law of quadratic reciprocity. What they are mod 4. So here, this exponent, maybe I should say, is determined, maybe I should say the exponent mod 2, but it's determined by pi and pi prime mod. So 4 is 2 squared. This is mod, let me move this all over a little bit. Determine mod 1 plus I to the 5th. And I on pi is, and 1 plus I on pi are also determined, for simplicity here, also by pi mod 1 plus I to the 5th. So in the supplementary law over Z, minus 1 on P depends on P mod 4, 2 on P depends on P mod 8. Okay, so I'm just giving a common modulus here for everything. Maybe in some instances, you can cut down the modulus to a lower power of 1 plus I, but it's analogous in the sense to ordinary quadratic reciprocity in the sense that the modulus to which the primes matter is a power of the even prime in the Gaussian integers. And so I'm not going to give the formulas here, but I'll just show you an example of coming back to the question about the Diophantine equation, but number being a square mod of prime in Z, if Z root D is a UFD, being equivalent to writing plus or minus the P as a norm, and you can get rid of the minus sign if you can write minus 1 in that way. So let's just do one example. Okay, so here's a theorem. If alpha in the Gaussian integers is not a square, this is like the D we had before, and when I adjoin the square root to Z bracket I, that this has unique factorization, it's a unique factorization domain, then for primes pi, in Z bracket I, alpha is congruent to a perfect square mod pi if and only if some unit multiple is x squared of pi is x squared minus alpha y squared in Z bracket I for some unit. For some unit u. And if I wanted to get rid of the unit ambiguity, what kind of condition should I want to impose? The analog last time was to avoid the plus or minus sign, I want to write minus 1. If I could write minus 1 as such a norm, I can massage it onto the right side, because product of norms is another norm. So the analog here, because I generates the units, the analog here would be we can avoid the U factor if the basic unit I has this form, obviously for new x and y. Okay? Then you can just write pi in the equation on the right-hand side. So let's do an example. Let's think about, and we'll end with this example. Let's think about x squared minus 1 plus I y squared equaling a Gaussian prime. So turns out, fact, this needs some algebraic number theory. If you take the ring Z bracket I bracket the square root of 1 plus I, so I'm taking the square root of a quadratic thing. This is a rank 4 ring over Z. I can get rid of I, because if I know root 1 plus I can square it and subtract 1 and get I. So this is the same ring. So this turns out to be a unique factorization domain. And I has this form. I wonder if anybody can figure out x's and y's that make this work. I'll just tell you. If x and y are both I, minus 1 minus 1 plus I is I. Yeah, right. So therefore, it is true that 1 plus I, by the same method we discussed earlier for the integers, that 1 plus I is a square mod pi if and only if pi can be written in this way in Z bracket I. So on the left-hand side is like the supplementary law for 2 being a square mod p. Is 1 plus I a square mod of prime? So let's look at an actual prime. So let's take the prime to be 2 plus I. This is a prime in the Gaussian integers. 1 plus I turns out to be congruent to 4. Mod 2 plus I. You can verify it because if you subtract the two of them, the difference as a Gaussian integer is divisible by 2 plus I. And I hope you all see that 4 is a perfect square. So we must be able to solve the equation x squared minus 1 plus I y squared equal to 2 plus I in Z bracket I. And indeed, there is a solution. I just had to hunt around by hand trying things out. An example, you take x to be 3 and y to be 2 minus I, it actually works. All right? And I'll do one more example, and then that'll be it. If we take the prime 2 minus 5I, turns out 1 plus I is a square. 1 plus I is congruent to 100. Mod 2 minus 5I. So we must have a solution to the equation x squared minus 1 plus I y squared equals 2 minus 5I. So we're kind of solving generalized Pell equations in the Gaussian integers by reducing it to a square condition mod a prime in Z bracket I. And you can use x equal 2 minus I and y equal 1. That actually works. Okay? So all this stuff we were doing with quadratic reciprocity over Z, you can extend it to other rings like Z bracket I, Z bracket root 2, and things like that. And the applications that we made over Z can be adapted to these other rings as well. So the scope of quadratic reciprocity goes way beyond just doing it in the integers, and I'll stop there. Thanks.